exist? Many people think that's a silly question. Don't you just need to look at a calendar or the clock on the wall to get the answer? But physicists are increasingly proving that they have reasons to doubt the actual existence of time. In the 19th century, Albert Einstein with the theory of relativity overturned our concepts of time. He proved that time is actually created by matter. Time does not exist independently of the universe but only appears with it. Einstein also proved that throughout the universe, time is only a relative thing. It passes slower for people on a spaceship moving near a giant black hole, or flying at speeds close to that of light. Therefore, there cannot be a present that occurs simultaneously for the entire universe as Newtonian physics was acknowledged. In quantum physics, time isn't even necessary to exist. All the fundamental equations describing the quantum world remain correct without the time variable. So, there may be places in the microscopic world where time truly doesn't exist. What would happen if one day physicists discover that time is meaningless, and everything in our lives is just endlessly repeating, instead of having a beginning and end as we once thought? Physics is in crisis. That's the truth we must face after more than a century. When scientists explain the universe with two extremely successful physical theories. The first theory is general relativity. The second theory is quantum mechanics. Quantum mechanics describes how things operate in the microscopic world of tiny particles. In contrast, general relativity describes the big picture of gravity and how objects move on a cosmic scale. Both theories work very effectively within their domains, but it's not hard to see that they have contradictions with each other. Although the exact nature of this contradiction remains something physicists debate, they generally agree that both theories will be replaced by a new, more comprehensive theory. This new theory is called quantum gravity, a theory that unifies both general relativity and quantum mechanics, allowing the isolation of everything in the universe that we know. Quantum gravity also allows us to explain things that the two old theories couldn't explain. For example, how gravity operates at the small scale of particles. In the past, many physicists have tried to build quantum gravity. The problem is to overcome the contradiction between relativity and quantum theory. The hope of achieving this has been placed in string theory, in which particles are replaced by vibrating strings in 11 dimensions. However, string theory also faces another difficulty. Although it provides many models that accurately describe how a universe like ours operates on an overall scale, string theory doesn't actually make any clear predictions that can be tested by experiments to find the appropriate model. This can be considered a failure of the theory, because in physics, a strong theory needs to do both things: explain the world and make predictions for that world about how things will operate in the future. This is precisely the reason we must study Einstein's theory of relativity, when he predicted the existence of gravitational waves 100 years ago, before humanity actually found and measured them in the universe. With string theory, scientists simply cannot predict anything. Therefore, by the 1980s and 1990s, many physicists became dissatisfied with string theory. They proposed a series of new mathematical approaches to try to build quantum gravity theory. One of the most prominent features among these models is introducing a phenomenon called loops into quantum gravity. These loops explain the structure of both space and time as a network of extremely tiny discrete components that have no beginning and no end. This seems to completely eliminate time from quantum gravity theory. Not only quantum gravity theory, some other physical theories that scientists are building could also eliminate the necessity of time. So now we understand that physicists are finding new theories to explain and predict the universe. And these theories might exist independently of the time variable. Now, suppose such a theory is proven to be true. Would it make our time disappear? The answer is quite complex, and it turns out it depends on and determines the meaning of our existence. We know physical theories do not include the appearance of any tables, chairs, or people. However, we still accept that tables, chairs, and people exist. Why? Because we assume such things exist at a higher level than the level described by physical theory. The existence of this table, this chair, and us humans is a holistic combination of billions of tiny material particles. Atoms, subatomic particles like quarks or electrons. But while we have a fairly good sense of how a table can be made from fundamental particles, we don't know how time could be made from something fundamental. So unless we can use the new theory to explain how time emerges, or how it is composed of something smaller, we can accept the existence of time. Conversely, saying time doesn't exist is like saying there are no tables in this world. Humankind might try to live in a world without any tables. But managing in a world without time seems like a disaster. Our entire current life is built on time. We plan for the future based on what we know about the past. We require people to be morally responsible for their past actions, with the purpose of reprimanding them later. We believe that humans themselves are agents. We can influence the causality of the universe. Because partly we can plan, act in the way we want. The principle of causality could be completely broken if time doesn't exist. Because what meaning does causality have when it is impossible to determine that the cause occurs first, and the effect occurs later? At that point, could trials punish a criminal for what they did in the past? T exists and their will didn't. The discovery that time doesn't exist would seem to make the entire world stop functioning. We would have no reason to get out of bed every morning when the alarm rings. So we must hope at least if there is a physical theory that eliminates the existence of time. It must somehow maintain the causal relationship, meaning that human consciousness must be an agent that makes a difference. Such a theory would tell us that physics is actually about causality rather than time. Causality is the fundamental characteristic of the universe, and only when that is true can the world and society we know continue to exist. Otherwise, we would simply fall into chaos, like the entire planet being shot out into space. When the gravity discovered by Newton no longer exists, there might be a parallel reality existing with us right here and now. We know that in a revolutionary effort, scientists want to unify two famous theories in physics, which are general relativity, describing the motion of the universe on a massive scale, and quantum mechanics, describing what happens at the atomic and subatomic particle level. The unified theory after construction will be called quantum gravity theory. It promises to allow us to explain almost every mystery in the universe, from the presence of dark matter, the flow of time, tunnels connecting galaxies through black holes, and even answer the question of whether we can travel back in time or to other multiverses. However, that also indicates that as long as quantum mechanics and general relativity have not been combined, the universe still holds many mysteries that humans are unaware of. For example, recently, NASA reported that something strange is happening to our universe. It is causing galaxies to expand faster than what scientists had previously calculated. And at the other end, on the quantum scale, a group of scientists at the University of Maryland discovered something even stranger. They saw a set of electric charges behaving strangely between two stacked graphene sheets. We know graphene is the thinnest material on the planet. It is only as thin as a single layer of carbon atoms, so it is also called a 2D material. When electric charges behave anomalously between these two 2D material layers, scientists believe they might be interacting as if in two parallel universes placed side by side. These interactions can be extrapolated to our four-dimensional universe. And if so, it is not impossible that our universe also has another reality existing parallel right next to it. That reality is happening here, right now, and is only obscured by some invisible barrier. But sometimes there are entities jumping back and forth between the two universes, the two parallel realities without our knowledge. The new research was enacted by Dr. Viktor Galitsky, a Russian-born theoretical physicist, specializing in quantum world research at the University of Maryland, USA. Together with his research student Alireza Parhizkar, Galitsky conducted an experiment involving two graphene sheets. Scientists placed one graphene sheet on the surface of another, creating an interaction model, and observed how electric charges moved through the sheets. Each of these graphene sheets is a single atomic layer of carbon, arranged in a repeating hexagonal pattern. They form a pattern called a moire pattern. Moire patterns form when there are two repeating patterns, anything from the hexagonal patterns of carbon atoms in graphene to window screen grids. When they overlap, they create overlapping twisted layers or stretch each other. Therefore, when two graphene sheets form a moire pattern, they affect the behavior of electric charges, especially the behavior of electrons. The charges jump back and forth between the two graphene sheets, and in a special case called magic angle graphene. When the moire pattern repeats over a length about 52 times the pattern length of the individual sheets, the energy level governing the behavior of electrons drop rapidly, allowing new behaviors to emerge, including superconductivity. Galitsky and Parhizkar argue that this physical phenomenon occurring in two graphene sheets can be explained as equivalent to a phenomenon occurring in two two-dimensional universes, where electrons occasionally jump back and forth between universes. The question now is whether a similar phenomenon occurs in our four-dimensional universe? Dr. Galitsky said, "We know this is an interesting and ambitious idea. In a sense, if that is true, it would explain a series of fundamental characteristics of our universe, such as the state of inflation when particles from another universe jump into ours." To prove this, Dr. Galitsky built a mathematical model, generalizing the case of two graphene sheets to more multidimensional universes, including our four-dimensional space. His goal is to see whether a moire pattern could appear there, and whether there is a possibility of a universe stacked upon us. Mrs. Hitchcock said we discussed whether it's possible to observe the physical phenomenon when two universes actually merge into one. If you want to understand what lies behind this question, first you need to know the dimensional length of each universe. This will be a problem because of the atomic scale of graphons. The unit of measurement we choose for them is intervals of 1/10 billionth of a meter. But that unit of measurement becomes useless when you want to measure the distances you see. For example, the length of a football field. It becomes even more useless when considering the scale of galactic universes. The unit of measurement also determines the accuracy of mathematical programs. Therefore, Galitsky and Parakhizkar decided to choose the blend length, considering the definition of the smallest length compatible with quantum physics. The blend length is also directly related to a constant called the cosmological constant, which is present in Einstein's field equations of general relativity. The Planck unit will be the best bridge for the two mathematical models that Galitsky built. Thanks to it, they established an equation describing relativistic effects and quantum effects. It shows that the influence of quantum fluctuations in the vast vacuum will affect behavior at the cosmic scale. Galitsky and Parakhizkar call this mathematical model gravity moire, and it creates a scenario in which two parallel universes coexisting according to Einstein's general relativity are placed side by side and interact with each other, like the two reference plates in the initial experiment. Dr. Galiski's work here is to examine the constants and cosmic lengths in each parallel universe he theoretically created.
Galiski found that if these two worlds interact with large cosmological constants,
they can overwrite the behavior of one universe onto the other, and override their own universe's constant to the other universe. Developing this theory, Galiski and Pajiska began building a new theory called the two-world theory. In it, they explain the existence of a dipole field. When two worlds exist in parallel where each world is a complete world by our standards, they both have their own matter, energy fields, and physical principles. The existence of the dipole field allows scientists to explain some phenomena. For example, the existence of light in the early period after the Big Bang. Therefore, Galiski is betting on his hypothesis. In the future, he will conduct more experiments to verify it. And who knows, when that is true, you might find another version of yourself right here, beside you. Everything is possible if there really are two universes existing as a moi pattern.
And when the invisible barrier separating them is removed, we will be able to see another version of ourselves.